Warning, the video you're about to watch contains mathematics at the level of precalculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosines River College in Sacramento, California. In this video, we're going to focus quite a bit on right triangle, non-right triangle trigonometry, and this is just a continuation of the law of cosines and law of sines, and we just finished doing a part 2 for applications of non-right triangle trigonometry. But navigation problems deserve their own video. Not that they're harder, that's not true. It's just that there tend to be a lot of them in trigonometry and in precalculus, and it's kind of important to take a few moments to talk about the language used in these problems. So you'll see words like heading, bearing, direction, course, true course, all this stuff. What does any of that mean? Well, it really, truthfully, honestly, depends upon who's defining it. And I hate to say it that way because usually in mathematics, we like a clear-cut definition. But I can tell you right now, my wife is doing pilot's license stuff, and her definition of these differs from some textbooks I've used in the past. So I'll just give you a kind of a heads up, forgive the pun. So heading, in my opinion, is generally measured from due north. So that's like if I said you had a heading, let me write that. If you had a heading of 10 degrees, that is from due north, you're tilted over by 10 degrees. Now, normally in trigonometry, you would never measure anything from the vertical axis, normally. But it turns out that when you're doing applications, you often do. So that would be a heading of 10 degrees, a heading of, let's say a heading of 210 degrees would be, again, measured from due north going clockwise. So there's 90, 180, and then 30 more. So this right here would be a heading of 210 degrees. So that's just a heads up about heading. And then bearing is the one that I'm going to focus on quite a bit. Bearing is what you would normally see in navigation for nautical navigation, where it's like north by so many degrees east or west, or south by so many degrees east or west. So again, bearing has the notation north by so many degrees west, or north by so many degrees east, or south by so many degrees west, or south by so many degrees east. You do not start with east or west. So do not say, oh, it's east by so many degrees north. That is not used. So we start with north or south and we end with west or east. This, it's very contextual. So just letting you know, if you're reading through a problem and they give you north by so many degrees west and they say the word heading with that, fine, just accept that. Everybody defines it slightly differently, and that's okay. This notation here should just tell you what's going on. So if, for example, I said, oh, I have an angle, it's north by 17 degrees west, well, that means I would face north and I would turn west. West is counterclockwise, I guess you could say, by 17 degrees. So that is north by 17 degrees west. If I said south by 17 degrees west, you would first face south and then turn through an angle of 17 degrees. Again, in these applications, you're measuring from the vertical axis, which is a rarity in mathematics, but that's the case in applications. It's just what we have to deal with. So let's go ahead and tackle a couple applications, and they're the ones that my students are going to see. So if I don't do a problem style that you're going to do, I apologize. So Alice sets off on her hike from the lodge at a bearing of south by 74 degrees west. After 3.4 miles, she changes her bearing to south by 13 degrees west and continues hiking for 6.8 miles. Find Alice's distance from the lodge at this point, and what is the bearing for her to go back to the lodge? So I've read the problem. I now need to draw this problem out. And this is critical that you pay close attention to what I'm about to say. Notice that she's turning south and moving. So I'm going to start by plotting something at the north end of my page. And also note that I plotted it kind of the north east of my page because she's heading southwest. So I'm giving myself room to draw. The next thing I want you to note is when I plot that point, I'm going to label it. They said she starts at a lodge. Fine, I'll call that point L. The next thing I'm going to do is put a very small set of axes on there. I don't need a massive set of axes. I just need the north-south axis and the east-west axis on there so that I could see, okay, she started her hike, she faced south and went and turned through 74 degrees west. So she faced south and then turned through 74 degrees to go west. So that's a 74 degree angle. Now I'm also going to go ahead, maybe I'll bring in a ruler here, and my ruler can actually do 74 degrees. So 90 minus 74 would be 16. So I want a 16 degree angle here. So in reality, this is 74 degrees. And I'm going to just say that I'll use black to sketch out her path. So she only goes 3.4 miles along here. So I'm just going to say, let me move this here, and I'm going to use the ruler to guide me a little bit. So I want 3, 1, 2, 3, and a little bit more. Okay. So we're just going to say that's a distance of 3.4 miles. I'm going to zoom in here, and I'm going to go ahead and erase that and extend my angle a little bit there. There's 74 degrees. Okay. Now, this is kind of a stopover point right here. She stops over just for a brief moment. And at that stopover point, she's going to now change her mind and go in a different direction. She changes her bearing to south by 13 degrees west. So in these problems, every time there's a stopover, I highly recommend drawing a very small set of axes on there. Very, very small set of axes, just so that you can say, okay, now it's like a little target. Right there, she's going to face south and then turn 13 degrees west. So again, I'll just use my ruler to do this. She'll face south and turn 13 degrees west. I can't get a nice 13 degree angle. So 90 minus 13 is, what is that? 77. So I want a 77 degree angle here. You don't have to worry about what I'm mumbling. I'm just getting this to go right. There's a 77 degree angle. And she's going to start at that angle. She's facing that angle, and she's going to hike for 6 point some odd more miles. I can't see it because it's in my way. 6.8. So 6.8 miles. Let me get this set up so that it's easy for me to do. Okay. And I'll zoom out a little bit because I want to go 6.8 miles. So 1, 2, 3, 4, 5, 6, and some change. Okay. I'm just being exact because I want to. I'm going to move that off the screen and zoom in. So again, this angle right here in blue is south by 13 degrees west. So that's a 13 degree angle right there. And the question is, when she arrives at this destination, which I'll plot in red right down here, the question is, how far is she away from the lodge? Let me go ahead and measure that out. I'm not going to measure that distance, by the way. I'm not going to say like, oh, let me use my ruler to find that distance. We're going to use mathematics. But we want to know what this distance is here in red. And we also want to know the bearing for her to go back if she did a straight directed distance walk back. So this is a big problem, but generally speaking, if you just follow my logic here and plot your points and your axes at each point, you'll be fine. In fact, where she ends, I'm going to plot a set of axes as well. So horizontal and vertical set of axes. All right. So let's see. What do we know in this problem? We know the distance here is, when I say here, I mean right here, is 3.4 miles. We also know the distance along the next path was 6.8 miles. So this is 6.8. But we don't really have any other information. We have some angles, and that's going to be helpful. So how are we going to use those angles to our benefit? Well, the answer to that is pretty, just involves a little bit of manipulation and thinking here. Honestly, I'd love to have this angle right here, because if I did, then I could use the law of cosines to find out what this distance is. If I had that angle, then I could find the distance using the law of cosines. Well, I kind of do have that angle. I have 13 degrees of it here. I have a 90 degree of it here, 90 degrees, and then what you think is an unknown angle there. But this is why I say, please draw axes at every single stopover point. Because that angle, this line is horizontal. That little angle right there, that little sliver of an angle, since geometry is a prerequisite for trig, you should know these are alternate interior angles. Those angles are the same. So again, maybe I should use a different color. This green angle right here and this green angle right here are the same angles. They're alternate interior angles because there's that transverse, that black line there, cuts through two horizontal lines. And so those angles will be the same. Well, let's see. This full angle right here is a right angle, but 74 degrees is taken on the first chunk of it. So this green angle here must be 90 minus 74, which is 16 degrees. Did I say 74? Is that right? Okay, yeah, 16 degrees. All right, great. So if that's a 16 degree angle, then so is this one. And now I know that the total angle right here is 16 plus 13 plus 90, which is going to be, what is that, 110, 119 degrees? Let me just double check my mathematics. 100, 110, 119, yes. Okay, so that is how these problems are done. Now I just want to find the distance. So let's go ahead and find that distance using the modified Pythagorean theorem, which is basically the law of cosines. We'll say that d squared is equal to the sum of the squares of the other two sides, 3.4 squared plus 6.8 squared minus twice 3.4 times 6.8 times the cosine of the angle opposite d, which is 119 degrees. Now all I need to do is take the square root of both sides and grab a calculator. And rounded to the nearest tenth of a mile, it's 9.0 miles. It's actually 8.956, but that rounds to 9.0. So 9.0 miles is how far she is away from the original lodge, right? She actually hiked, 10.2 miles? But she is a distance of 9 miles away, just direct the distance. So we've answered the first part. Now we need to know, how is she going to get back? If she wants to walk on that red line all the way back, how is she going to do that? What is the bearing? In other words, is she going to first face north or south? Well, that's a silly question. She's totally going to first face north. So she will, I'll use green for this, she'll face north first, and then she'll turn through this angle right there. Well, I'd love to know what that angle actually is, and I kind of do. If you take a look at, again, that vertical line in green there, the angle that this is right here is equal to that 13 degree angle with the vertical right here. They're alternate interior angles again. That's why, again, I tell students, always draw these axes at every stopover point, because those alternate interior angles are going to be super powerful. So I know that small sliver is a 13 degree angle. And now I just need to know, what is this other angle right here? And that will require, possibly, let me just see if it will require anything. Yeah, I was just checking to see if I could use another little geometry trick for that, but I can't. That will require the use of the law of sines right there. So I'm going to go ahead. I'll just draw out or label things so that you can see what I'm talking about. Actually, I don't need to label anything. You can actually see this. The sine of that angle, which I will call that angle, let's just call it theta. The sine of theta is to its opposite side, 3.4, as the sine of 119 degrees is to its opposite side, 9.0. And again, that 9.0 is an approximation. So I'm going to use the exact value in my calculator, but this tells me that theta will be sine inverse of 3.4 times the sine of 119 degrees divided by my rounded value, which I'm not going to use. I'm going to use my calculator's exact value if I can. So grabbing my calculator, here I go. I get roughly 19.4 degrees. Now, here's where some people just get kind of frustrated because they're not paying attention to something. So I'll have students that say, oh, for Alice to get back, it was Alice, right? Yeah. For Alice to get back to that lodge, she faces north and turns through 19.4 degrees. That's not true. She has to turn through 13 plus 19.4 degrees. So she'll face north and turn by 32.4. Yeah, 32.4. My hand is moving that. Degrees eastward. East is clockwise there. This is east. That is west. So let me just double check. 32.4. Yes. North by 32.4 degrees east is her bearing to go back to the lodge. So we have finished that part as well. That's a big problem. I mean, big exercise to go through, but one of the most important ones, in my opinion, to showcase true understanding and true critical thinking skills in a trigonometry course. And of course, you could be watching this if you're taking pre-calculus as well. So these are wonderful problems. Highly recommend you practice as many as possible. So why not do another one? So this is the last one here. A helicopter makes a forced landing at sea. The last radio signal received at a navigation station gives the bearing from the station to the helicopter as north by 55.4 degrees east at an altitude of 1,050 feet. That means that the helicopter was last seen at that altitude. An observer at the station confirms that the angle of elevation to the helicopter just before descent was 22.5 degrees. How did that person know? Have no clue. Luckily, there is a rescue boat due north of the station, and the bearing to the helicopter from the boat is south by 56.4 degrees east. How far is the boat from the crash site? This is a very complex problem. I've read it, but if you're like me and you need to kind of draw things out, you should. Right? This is not very visual because I didn't give you a visual. So I'm going to go ahead and start drawing. I do know one thing. From the station, they're going to look northward and to the east to look at the crash site. From the rescue boat, they're going to look southward and east to the crash site. So I'm going to leave myself room to the east for the visuals. And I'm going to draw just a vertical line here. And the reason why I'm drawing a vertical line is there's a rescue boat due north. Whoops, that was supposed to be a highlighter. There's a rescue boat that's due north of the station. So I'm going to call this point over here B. That's the boat. And I'll call this point S for the station. Now, from the station to look at the crash site, they look, let's see, bearing from the station to the helicopter as north by 55.4 degrees east. So they're going to look northward toward the boat, honestly, and turn through an angle of 55.4. Now, if you're looking at my ruler, that's, if I stopped here, I'd be, maybe I should say, if I stopped here, I'd be wrong because that's this angle being 54. We want this angle to be 54. So we need to take 90 minus 54 for me to actually figure out what that is. That's just something, or 55, I'm sorry. That's just something that I have to do on my end. You would normally not have to do that within your problems, but I'm just trying to be exact. So there you see it says 34 because 90 minus 34 is, what is 90 minus 34? It's 56. And so this is them staring through an angle, looking north and staring through an angle of 56.4. I just couldn't get the 0.4 on there, but there's 56.4 degree angle. All right, great. And then from the boat, let's go ahead and highlight what I'm talking about now. So we've taken care of that first part. Observer from the station, blah, 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 blah. Okay, bearing to the helicopter from the boat is south by 56.4 degrees east. Okay. Oh, that's my problem. Okay, give me a moment because actually I should have done this one. North by 55.4. So let me just fix this. That's roughly the same anyway, so I'm just calling it 55.4. North, turn 55.4 degrees east. That's what they look at from the station. And now from the boat, that's this part right here, it's south by 56.4 degrees east. And there we go. You have the boat, they face south and turn through an angle of 56.4 degrees east, and they spot the helicopter crash. And then the people at the station face north and turn through an angle of 55.4 degrees east, and they see the crash. I'll erase all these extra little extraneous lines. So there is the triangle we're worried about. Let's see what else we can work with here, because they gave us a lot of information, right? Maybe I should leave highlighted the things that we kind of talked about. So we know the helicopter made a forced landing at sea. Great. That information has already been taken into account. We know that the bearing from the station to the helicopter is this north by 55.4 degrees east, and we've done that already. We haven't taken care of that altitude. That's going to be important. We didn't take care of the angle of elevation, 22.5 degrees. So we'll take care of that in a moment. We did label the rescue boat due north of the station, and we labeled the bearing from the boat to the helicopter. How far is the boat from the crash site? So we want to know what this side length, I'll draw it in red here. We want to know what that side length is. Okay. And we'll call that side length S because it's opposite angle S. And I'll call this angle S. I'll use little capitals there. All right, so that's what we want to find. Well, notice you only have two pieces of information here. There's no way you can find out what that side length S is right now. There's just no way at all because I didn't give you another side length to work with. So we must be missing a piece of information, and we are. If you look at the stuff we haven't highlighted, that's going to give us a second triangle. So we know that, I need to get a different highlighter here. We know that a person at station S here saw that the helicopter crashed at an altitude of 1,050 feet was when they started making the descent, and that was an angle of elevation from the station of 22.5 degrees. So what I'm going to do, this is what I do in calculus. This is a top-down view right here. We're looking kind of an elevated top-down view of the ocean, but we have a side view as well. This is so I don't have to draw in 3 dimensions. And our side view is going to be this side right here from the station to the crash site. And that side view is going to look like this. I'm going to take that side. Let me go ahead and just do this. And we know there was a helicopter. So I'm going to call this point over here the station. And this point, this is the crash. So this is the point C. That's where it crashed into the water. But we knew that before it crashed, it was at a certain altitude. And that altitude was a 22.5 degree angle from the station. So let me go ahead and just draw that in. We'll say that's it. Just like that. And I don't need this ruler anymore. I'll just kind of shade that in and I'll erase this piece. Great. So we know that there was an observer at the station who said, oh, the angle of elevation to the helicopter right before the crash was 22.5 degrees. And we have the data from the helicopter saying that this altitude initially, or at time of crash, or right before crash, was 1,050 feet. Let me just double check that number. Yes. All right. So we have a side in blue here that is shared in common with this triangle right here. They both are the blue side. And note, I can use right triangle trigonometry to find the length of that side. So I can find this length right here. That would be the distance from the station to the crash site, which is not what we're being asked for, but that's okay. It'll help us out. So what trig function relates this angle with this side and this side? If you said tangent, you would be absolutely correct. The tangent of 22.5 degrees is equal to opposite, which is 1,050 feet, over adjacent, which is L feet. I'll solve for L here. L is equal to 1,050 over the tangent of 22.5 degrees, that is. And now I know what this length here is. This length is that number. I'm just going to write it as 1,050 over the tangent of 22.5 degrees. Now that I know this length, I can actually find this length. And I don't have to use law of cosines for this. I use law of sines, because side length S is to the sine of its opposite angle, which is 55.4 degrees, as side length L is to its opposite sine of its opposite angle, which is 56.4 degrees. We know what L is. It's a number we can compute. So I'll multiply both sides by the sine of 55.4. So S is equal to L times the sine of 55.4 degrees divided by the sine of 56.4 degrees. And again, L is just this number right here. So we have everything we need to compute that. I'm just going to grab my calculator and do it. And it's approximately 2,505 feet away. It's really half a mile away. That's actually not that big of a deal. But anyhow, so that's how you would do. This is a very complex problem. In fact, this style of problem generally comes with a picture, but I just didn't want to break copyright, so I didn't actually paste the picture here. But this is a really, really good problem. It's great because when you reach calculus, you do a lot of three-dimensional work. And so you need to get used to having two different pictures, one for a top-down and one for a side view. That way you don't have to draw in 3 dimensions. Just my advice. Anyhow, that does it for this video. We are completely done with applications for laws of cosine and stuff like that, at least in this part of the course.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.